Welcome. In this session on natural deduction, we'll explore a formal language for predicate logic. And this formal language, we'll do it informally. And by informally, I mean we won't actually use a meta-logic and Zermelo-Fraenkel set theory and so on. What we'll do is we'll just use English. So when we had propositional logic, all we had were propositions and the operators of negation, disjunction, conjunction, and implication to deal with. Now we have these ideas of objects or variables, and we have predicates. So we need a little more linguistic machinery. So to start with, what we'll do is we'll say that variables are written, so we'll use the last part of the Latin alphabet. So we'll use things like X, Y, Z, W, and so on. And these are, let's put these in quotes so that we're not defining them, we're just referring to them, these are things or objects. And so variables are our first idea. The next is a constant. And a constant, for example, we might identify one particular object as being Socrates. And we won't use constants a lot, but when we do, we'll use the first part of the Latin alphabet. And these are often written as a nullary, or you could also think of it as a zero argument function. And what that means is that it's a function that doesn't take anything in. So it has zero arguments, or we might say that it has null. Instead of being unary or binary or ternary and so on, mathematicians will often call it nullary. And what that means is if it doesn't take an argument and it maps to something, then it must be mapping to a thing or an object. And so it'll always return the same one. A function, so a function for us has zero or more arguments. And we'll say that this maps to objects. And so, for example, we might say f of x or f of x, y, or we might have some term t. So we might have t1, t2, t3. And so this maps from the arguments to the objects. And the arguments are terms. Well, we didn't define term, did we? So let's try that. So what's a term? So a term is a variable, a constant, or a function. And once we allow a term to be a function, you can see that if a function maps a term to an object, then you can have these be nested or even recursive. So recursive functions are certainly possible. We're simply noting that that could happen. It's not that we'll actually use that in any of our subsequent sessions. So let's draw a little line here. And now, the next thing that we have is a predicate. So a predicate maps let's say 0 or more terms to a set. Now, that means that if a term maps to the set, we'll say the predicate is T, and otherwise it's F, false. What we're doing here is perhaps a little unusual. That is, there are two ways that we could define a predicate. So we'll say this is an extensional. Extensional definition. And an extensional definition is one that is defined in terms of a set, and an intentional definition is one that is defined in terms of intent, that is, in terms of meaning. And for our purposes, this extensional definition will be really useful. So, for example, if we have the set of all, so example that we've already come across is, suppose we have a predicate H of an object, and this maps to the set of humans. And so if we insert Socrates in here, then Socrates will evaluate to H. Well, yes, that's one of the things that we would like Socrates to map to. And if we were to insert a dog in here or a rock, that would not map to the set of humans, and so we would say that that predicate is false when applied to that term. Next, we need to define what we mean by a formula. When we were in propositional logic, a formula was relatively easy to define, and that was a formula was either a term, a literal, or it was the result of applying operators and parentheses. So now what we have to do, we don't have propositions anymore, so we start with the predicates. So formula is a predicate is a formula. And now we'll say we want to have negation. So if phi is a formula, then the negation of phi is a formula. And then we need our other logical operators, and so we'll say if phi and c are each formulas, then we'll say that if we take phi disjoined with c, if we take phi conjoined with c, and if we take phi materially implies c, are formulas. And so what we've done with these rules is we've more or less said, in place of a proposition, we're going to use a predicate, and then we're going to build formulas in all of the usual ways. So what that implies for us is, or means, that this logic will include everything that we've had in propositional logic. So now we also have to have quantifiers. So what we can say is that if x is a variable and phi is a formula, then we would say that for all x phi and there exists X phi are formulas. And as we discovered with propositional logic, once we have the syntax, we can perform all of the proofs that we need. What's missing that we'll have to defer for sessions later on in this course is the semantics. And the semantics are going to be much different than we had for propositional logic. And a lot of it will involve the idea of this universal quantifier and this existential quantifier. But for now, what we can do is we can understand that this completely describes all of the syntax that we need for the subsequent sessions.